get started. Good afternoon, everyone. I'm the instructor, Daniel Ling. In the lecture today, we are going to talk about linear models for regression. We would like to develop some linear model to carry out one of the important machine learning tasks, regression. In the last session of today's lecture, we are going to announce homework number 1. Okay, let's begin with a quick review. In the previous week, we talked about the task of regression. So in the following slide, I'm going to use capital N to denote the number of training data we have, because this is a supervised learning task. So we have the training data as well as its ground truth. So we use xn to denote one of the training data, its feature vector. Also, we have its ground truth, a real value in the regression task. So this is the example of a regression task. This is a one-dimensional regression task. One point corresponds to one specific training data. We project the data onto the x-axis. We get its one-dimensional input, its feature, its input. If we project the data onto the y-axis, we get its ground truth, its target value in regression. So given a set of training data, our goal is to fit a regression model. In this chapter, we currently discuss linear model. So linear model is linear with respect to the input dimension. Therefore, it is a straight line. So given a lot of training data, we can fit a straight line for regression. After getting this model for an arbitrary input, say this is a new input, we have its one-dimensional feature. So based on the regressor, we can get its output. So we have someone's income, we can estimate his or her degree of happiness. This is an application of regression. In this chapter, we talk about linear model. So this is the standard formulation of a linear model. Let's look at the notation. Y is used to indicate the regressor. Y, the behavior of Y is controlled by its parameters. The set of parameters is denoted by W. So given an X or given a training data point, X is the input, Y of X is its output. Let's look at the characteristics in the linear model. So as you can see here, the one-dimensional real value output is linear with respect to the input dimension. This data lie in a capital D dimensional space. So this is its feature vector. The output is linear with respect to the input elements. This is the reason why we say this is a linear model. The fitting power of linear model is insufficient. Therefore, we need to address this problem. In the previous week, we talked about how to extend the power of a linear model. We still want to learn a linear model, but we want to address the nonlinearity properties in the data set. To address this problem, this is a smart way. Here, we apply a set of nonlinear basis functions in advance. For learning a regressor, we want to optimize W. However, before optimizing W, we firstly apply a set of nonlinear basis functions to X. Each of the nonlinear basis function consider nonlinear mapping. We can map a feature vector X to a one-dimensional element. In this formulation, we employ a -1 basis function. So one particular basis function is denoted by phi j. Phi j is applied to the feature vector and the output, and give a one-dimensional output. So after projection, we transform the feature vector from the d-dimensional space to a n-1 dimensional space. In the new space, we still learn a linear model, but it is equipped with nonlinear fitting power because we have nonlinear transport data in advance. Okay, so based on this equation, this is the extended linear model. We still learn the linear formulation, but we have the nonlinear fitting power. Here is an impressive example. In this example, we are given a set of training data. Each yellow triangle is used to indicate one particular training data. So you can see this is the distribution of the training data. If we still use a linear model and we directly apply a linear model to the training data, as you can see, the result is not good enough. This is because the distribution is nonlinear with respect to the input. In this figure, we consider to employ a nonlinear basis function. So this is the first nonlinear basis function. By one here, the red curve is the first nonlinear basis function. The second one, the third one, and totally we have 8 basis functions. This is the formulation for the linear regressor. We learn a weight for each nonlinear basis function. Say for the nonlinear basis function y2, we learn the importance of this basis function. So we learn a W2. So if we calculate the multiplication between W2 and phi2, phi2 is here, and if we multiply phi2 by a certain weight, W2, we get this one. Okay? So this is W2 phi2. This process is repeated for each basis function. It turns out that if we calculate the summation of this term, we can get this regression model. This is a simple but representative example. In this example, you can find that just employ a nonlinear basis function. Even for a linear model, we can carry out satisfactory regression for nonlinearly distributed data. 各位同学，我前面讲的这些就是上周讲过的东西做一个复习。从这个投影片第8页是上周之前讲的，接下来要讲的是新的东西那我们的数学是等一下讲的都会从这一个出发这个就假设大家有了解就是说我们在学习一个线性的模型，但是呢，因为它的 fitting power 的不足，所以呢，我们事先用了这个nonlinear的方式把资料呢从原来的低维度空间这个 x 呢，它原来是在大低维的空间，然后呢把它投影到一个一维的空间，它可能是用非线性转换，就像刚刚的例子，用高斯的方式做转换。那转换完了以后呢，每一个 phi j 是 dj 的 basis function， 它都会把资料投影到一维。那我们总共学习的 n 减1个 basis function， 所以我们就把资料投到 n 减1维。那在这个情况之下，我们在这个新的 n 减1维的空间里面学一个线性的模型。那这个具体的这个数学式的例子呢，可以由这边来呈现 到目前为止呢，都是复习上个礼拜的东西。那接下来我们要讲新的课程。Okay, the following course is a bit complicated, but I will try my best to express them clearly. So let's look at this statement. We make the assumption that each observation is sampled from a deterministic function with an aided Gaussian noise. So what is the meaning of this statement? Let's look at this question. An observation is a training data. So T is the observation. We have its ground truth value. It is an observation. And a deterministic function is given here. A regressor is a deterministic function. If we apply the regressor to the training data, so this is the output of this deterministic function. What is the difference between observation and the prediction? We make an assumption. Please notice that this is an assumption. Layer difference is a zero mean Gaussian. It's a zero mean Gaussian. So this is a deterministic function. It is a fixed value. Epsilon is a distribution, a zero mean Gaussian. So what is the sum of a fixed value and the distribution? Actually, we just shift the mean of the Gaussian distribution. So on the right-hand side of this equation, it's still a Gaussian, but its mean will be located here. So this is so we will, based on this observation, we have this equation. Actually, we expand this equation at least 3 times in the previous lecture. So this is a conditional probability. Let's look at the element here. W is a regressor. It is a linear model currently. We apply the regressor to one particular input to carry out regression. And the T is the ground truth. In other words, this conditional probability is used to express how well this training data could be regressed by this regressor. If this regressor can well predict this training data, the probability should be high. Otherwise, it should be low. So its corresponding figure is given here. This conditional probability is formulated as a Gaussian. So given the regressor, the red curve here, and given one particular training data, x0, if we apply the regressor to the training data, we get its prediction. So if the ground truth is around the prediction, we say this data has been correctly or accurately predicted. So its probability should be high. This is a Gaussian distribution. If the ground truth is approaching the prediction, the probability should be high. Otherwise, the probability decrease exponentially. So this is the meaning of this equation. If the ground truth is around the prediction, around the mean of the Gaussian distribution, it should be high. The probability should be high. Otherwise, the probability should be low. 这边我用中文讲一次哈，因为这个数学是基本上之后就会这个 chapter 基本上都在用这个数学式。那这个数学式呢，上周有讲过若干次。那我这边再讲一次，就是这边呢，我们要定义一笔资料的 likelihood，就是 我有一个 regressor W， 那我还有一笔资料，一笔训练资料 X 跟 T， 那我要定义这笔资料跟这一个回归器这个 regressor 的 likelihood。如果呢，就是如果呢这个 regressor 有办法把这笔资料回归的很好，那它的几率就要很高。反之，如果这个 regressor 没有办法把这笔资料回归的很好，这个值就要低。OK， 那为什么它就设计成这样子呢？为什么设计成一个高斯分布，然后它的平均值就是在预测值这边，就是达到我刚刚所讲的这个目的呢？我们来看我们有一个 regressor， 就是红线这条线那如果我们今天考虑一笔特定的资料 x0在这边，那我们怎么做回归呢？就把它投影到这个 regressor 这条红线这边，然后再把它投影到 y 轴。所以这个是这个 regressor 预测出来的结果。这个 regressor 红色的这条 regressor 预测 x0这个点这笔资料预测出来的结果是在这边。那什么叫做它预测的很好呢？什么叫做它预测的很好呢？就是呢，这笔资料的正确答案就在这个附近。这样子呢，就代表这笔资料被预测的很好。那所以呢，你可以看到，如果 ground truth 就是在绿色这条线的时候，它这条蓝色的高斯分布它的几率就很高。反之，如果呢ground truth 在很远的地方，在很上面或者是很下面，离这个预测结果一点都不近，那在这个情况之下呢，它的几率就要很低。所以你可以看到这条蓝色的线，实际上就是这边的高斯的分布。那它的中心点呢，就是在预测的地方。Okay, so far I give the definition of the likelihood of even a training data in the regressor. Please remember this expression because we will use the definition of likelihood in the remaining chapter. Okay, in the previous slide, we talked about the likelihood for regressor and training data. In practice, we have a lot of training data. So we have untrained data. For each training data, we can calculate its likelihood. Here we make the assumption that training data are highly independent and identically distributed. So the likelihood for the whole training set, is the product of individual likelihood because all the training data are independent and they are sampled from the same distribution. So they are sampled from the same distribution, so we share the common variance and the common W. And they are independent, so the likelihood of the whole data set is the product of individual likelihood. So this notation is used to specify the likelihood of the regressor and the whole training data. We would like to find a W that can maximize the likelihood of the whole set. However, it is difficult to optimize this equation directly because it involves the product operator. To address this problem, we apply a logarithm, a log operator to the both hand side of the equation. So we apply log operator to the left hand side of this equation. It becomes log likelihood. If we apply the log operator on the right hand side of this equation, the product operator becomes the sum operator. So this is the reason why we apply the log operator. So it is straightforward to have this equation. Now let's look at how to derive from this expression to this one. I write down the proof here. N is used to indicate Gaussian distribution. This is the definition of the Gaussian distribution. Gaussian distribution is controlled by two parameters, mu and the variance sigma squared. So in this equation, sigma squared is beta inverse, and mu is W transpose phi. So we substitute their definition into the definition of Gaussian distribution. We get this one. If you apply log operator to this expression, we will get 3 terms. So this is how to derive from this expression to this one. Okay, so let's look at the equation. This is log likelihood. Our goal is to find a W that can maximize log likelihood. On the right-hand side of this equation, there are 3 terms. You might notice that the first 2 terms are irregular to W. W is not present in the first term and is not present in the second term. So if you want to optimize log likelihood, we just focus on the third term. So what is ED? After some derivation, you can find that ED is either here. So what is ED? Actually, this is the sum of square error. So in this slide, we will get the conclusion. We want to optimize a regressor, a linear regressor, by maximizing the likelihood. We will have the least square solution. It is equivalent to minimize the sum of square error. So this is the conclusion I mentioned in the previous slide. We want to have the ML solution, maximum likelihood solution. After some derivation, we can prove that the optimal solution is equivalent to the solution that is obtained by minimizing the sum of square error. 这边我用中文试着再讲一次哈，所以这边的数学事情比较多一点点还是希望大家可以了解。我们在前一页投影片讲过单独一笔资料的 likelihood， 然后呢，我们的目标是要学得 W 是要学这个 linear regressor 的它的参数。那我们试着呢让这个资料的 likelihood 最大化。那一个整个资料集的 likelihood 呢，因为资料是 IID 的，所以呢，这些那个整个资料的 likelihood 呢，就是每一笔各自资料的 likelihood 做连乘而得。那为了解这个最佳化问题，我们要求得一个 W 可以使得这个东西最大化。那就像上个礼拜所讲过的，因为 log 是一个 monotonically increasing 的 function， 就是它是一个严格递增函数，所以呢，你取完 log 以后呢，它的最佳解就是取完的 log 的 log likelihood 的最佳解跟这个 likelihood 的最佳解是一样，所以你要找它的最佳解，既然跟它的这个最佳解是一样的，那我的运算下面的这一个，因为呢，它的不会处理到连乘的这个问题。那我们就把这个 log likelihood 呢，这个东西呢，经过了上述刚刚用英文讲的一连串的推导，那最终的结论呢，就是这一个 log likelihood 呢，会变成这3项。那我们的目标呢是要学 W， 可以发现呢 W 跟这一项无关，也跟第2项无关，它只有跟第3项有关。那第3项的定义写在这边。那这个时候发现了什么事情呢？我们要最大化 log likelihood。那实际上呢，就是要最小化 sum of square error， 前面有个负号在这边所 所以我们要让这个数学系越小越好。那这个跟我们呢在第一个 chapter 所学到的这个 sum of square error 呢，在这边呢是等价的。Okay, so we find the equivalence between the optimal solution using the two different formulations. In the following, I'm going to specify a method to carry out optimization. Okay, so our goal is to optimize W by maximize log likelihood. In one of the famous or representative optimization solver is gradient descent. So we calculate the gradient of log likelihood with respect to W. Let me go back to the previous slide. So this is log likelihood. We want to calculate the gradient of log likelihood with respect to W. Since the first two terms are irrelevant to W, so the gradient of the first two terms are zero. We just consider the third term, and the definition of the third term is given here. As you could check, it is differentiable with respect to W. So after calculate the gradient, this is the gradient with respect to W. In the second step, we set the gradient to zero to get the necessary condition for solution to be optimal. So we set the gradient to zero. So based on this equation, we can identify W, the optimized W. Let's look at the reason why. In this equation, Tn is the ground truth, so we have the ground truth before training. Phi of xn, it is the feature representation of the training data xn, so we also have this term. Let's look at the term inside the parentheses. We calculate the outer product between we calculate the outer product of vector phi of xn. It is known in advance, so we can calculate its outer product and calculate the summation. So in this equation, the only unknown is W. Therefore, after some rearrangement, we can get the optimal solution of W. So this is how to use gradient descent, or how to use setting the gradient descent, setting the gradient to zero to get the necessary condition for solution to be optimal. 各位同学，我们接下来这边讲的那个东西呢，是在这个 chapter 里面呢，很常用来解这种最佳化问题。我们刚刚说，我们要的解呢，我们要解的是 W， 那它是可以把 log likelihood 最大化。那这边用的技巧呢，或许大家已经有听过，或许已经会使用。就是呢，我们先把这整个 log likelihood 对 W 做微分。那我刚刚前面呢，用英文讲的时候呢，有跟大家提到，比如说这一个就是 log likelihood， 那要对 W 做微分。那前两项跟 W 无关，所以微分了以后就等于0。所以我们要考虑的就只有第三项。那第三项它的定义在这边嘛 ，ED 它的定义在这边嘛，那这个定义呢，你会发现这个对 W 来说是可以的，所以我们可以为它算它的 gradient 可以算它的 gradient。那我们把 gradient 设成0，算出来的这一串很长的东西，把它的 gradient 设成0，为什么就可以得到这个最佳解的必要条件？为什么在这个点如果我说它是最佳解的话，它必定 gradient 是等于0呢？
因为呢 gradient 就是指出某一个方向，沿着这个方向的地方走的话，这个值呢会增加，沿着它的反方向走的话，它的值会减少。所以当一个 gradient 不是等于0的地方的时候，你沿着这个不等于0的 gradient 的反方向走，你还可以让这个值呢再更低。所以呢，你要说这个一个解呢，它是最佳解的必要条件的话，它的 gradient 势必得等于0，不然它不是最佳解。那我们把这个 gradient 设成0了以后呢，这一串数学式乍看之下很复杂。但是呢，就像如同刚刚我用英文所说的，这里面每一个 element， 不管是光数的 Tn， 或者是每一笔资料它的 feature vector， 这个事先我们都知道的。那所以这个等式里面呢，唯一不知道的就是只有 W 而已。所以经过了一些移项以后，我们就可以得到W 的最佳解。这个就是如何使用 gradient 等于0的情况之下，得到最佳解的这个最佳化的技巧。So in the following, I'm going to specify the compact representation for the solution. So to begin with, let's define a new matrix called design matrix. So this is a large matrix. There are n rows. This matrix has n rows, one for each training data. So as you can check, in the first row, the input to the basis function is x1. So this is the first row for the first training data. Since we have capital N training data, this is, in other words, this matrix has a row. And this matrix has n columns, one for each basis function. So in the first column, we consider the bias term y0. In the second column, we consider applying basis function phi1 to the whole training data. So this is how to control each row or each column. So its size is n by n, the number of training data by the number of basis function. This is a design matrix. We use capital phi to indicate this design matrix. Okay. In the previous slide, we talked about we set the gradient to 0 in order to get the optimal solution. I write down the equation here. Okay. To have a compact representation, let's consider how to derive from this equation to this one. Actually, I provided 2 hints here for your derivation. First of all, let's look at this term. So after some derivation, we can use a design matrix to represent this term. It is phi transpose t transpose. How to prove this? Actually, you can check element by element. For example, we consider one specific element in the ith row and the jth column. So we check the value for this element, and then we can check the value in this representation. So you can prove their equivalence. This is how to prove this derivation. So this term has a compact representation given here. Let's look at the term inside the parentheses. I write down the terms inside the parentheses here. We calculate the out product for a feature vector of a specific training data, and we also calculate the summation. By using the same technique, you can check the equivalence from this one and this one. and you can find it. What is the definition of this? Actually, it is phi transpose phi. So the term inside the parenthesis becomes phi transpose phi. So you substitute the two derivation result into the original equation, we will get the closed form solution. We have the closed form solution for the regressive W.
这页投影片跟前页投影片主要是在讲说，在这边呢，我们刚刚提到的这个令 gradient 等于0，我们就可以得到最佳解。这个其实事实上事情到这边就已经结束了，我们就可以解出来 W。但是为了呢，让这个数学式呢看起来比较 compact 一点，以及为了后续的分析，那我们试着呢，用一个比较精简的方式来表达。那为了要比较精简的表示呢，我们介绍一个新的 notation， 我们用大写的 phi 来代表这个所谓的设计矩阵design matrix。那这个 design matrix 它有多大呢？它总共会有 n 个 row， 你可以看到呢，第一个 row 就跟第一个 data 有关所以呢就跟 x1 有关。第二个 row 呢就跟第二个 data 有关。所以你有几笔资料，你就有几个 row。那你有几个 basis function， 你就有几个 column。所以我们总共有 m 个 column， 主要原因是因为呢，我们总共有 m 减一个 basis function， 还有一个BIOS 统在这边，所以总共呢就是有 n 个 column。那大家先把这个定义记一下它就是 n 乘以 m 的矩阵。n 是资料的笔数，训练资料的笔数 ，m 呢是的这个basis function 的个数。那我们刚刚说，这个设令它 gradient 等于0的时候，我们就得到这个等式。那基本上我们就可以来解这个 W。但为了要有一个比较就是比较精简的比较 compact 的 representation， 那我想要把这个design matrix 把它引入。那怎么引入呢？这边我用投影笔画的这一串呢，经过了一些推导它就是可以用这个 design matrix 来表示。这个 T 是 transpose 意思有 phi transpose T transpose 这样子。那这个大括弧里面的这一串也是经过了推导以后呢，它就变成的是这个设计矩阵 design matrix 的 transpose 再乘上这个 design matrix 这样子。所以你这边有两个结果这边第一个结果，那这个第二个结果分别带入原来的式子，然后再做一些移项，做一些重新整理你就会发现原来在做这个 maximum likelihood 的 solution 的时候呢，我们其实是有一个 closed form 的 solution 是长得像这样子。Okay, maybe some of you observe that we need to calculate inverse to get the optimal solution. One question may arise. We need to calculate the transpose, the inverse of this equation. It is required that this matrix should be invertible. Actually, we cannot guarantee this matrix is invertible. However, we can find that in most cases, this matrix is invertible. Why? Let's look at this assumption. We assume the design matrix has linearly independent column. In most cases, this assumption is true. This design matrix has n row and n column, and typically the number of training data should be larger than the number of basis functions. Therefore, in most cases, phi has linearly independent column. So based on this assumption, we can prove that phi transpose phi is invertible. How to prove this? Actually, we will use a contradiction method
to prove this property. So we would like to use contradiction to prove this property. So in the beginning, we suppose that phi transpose phi is not invertible. It is not invertible. So we know since a square matrix is not invertible, the dimension of its neural space is at least 1. The dimension of its neural space is at least 1. So we can find a non-zero vector, and the phi transpose phi v is equal to 0. Okay. Based on this equation, we multiply both hand sides of this equation by v transpose. So we get this equation. After some rearrangement, it becomes the square 2 norm of phi v is 0. This is square 2 norm. Therefore, phi v is 0. We know what is phi v? Actually, it is a linear combination of columns in phi with the coefficient given in the vector v. So we can conclude that phi columns are linearly dependent. So the contradiction happens. We make the assumption, but the result is a contradiction. So based on this result, we can prove that phi transpose phi is invertible in this case. So we can calculate the inverse of this matrix and get the solution.
这页投影片我用中文讲一次因为我知道这个用英文有时候可能听得没有那么清楚。就是呢，我们刚刚讲了蛮久的，但最终的结论就是呢，这个 W 它有一个 closed form solution。那写在这边的 closed form solution 的时候呢，大家可能就会有一些迟疑了。为什么？因为我们要算这个矩阵，实际上这个就是一个方正的 inverse。那并不是所有的方正都是 invertible。那要是它不是 invertible 的话，我们就没有办法算它的解答。那好在呢，大部分的情况之下呢，这个方正是 invertible 的。为什么这么讲呢？因为呢，只要呢 phi 它的 column 呢是线性独立的，那我们就可以证明这个 phi transpose phi 是 invertible。那什么时候是这个 phi 它是线性独立的呢？它的 column 线性独立的呢？我们知道这个 phi 呢，它是一个 n 乘以 n 的一个矩阵。那 n 呢是这个训练资料的笔数，那 m 呢是 basis 的个数。那在大部分的情况之下，训练资料的笔数常常是比这个维度还要比这个 basis function 还要多。也就是说呢，大部分的情况之下，这个 phi 呢它是会有线性独立的 column。那只要有这个条件的话，这一个 phi transpose phi 就是 invertible。那为什么呢？我们是透过刚刚的这一系列的证明，我们用矛盾证法，就是说呢，我们宣称就是只要它是有线性独立的 column， 这个东西phi transpose phi 就是 invertible。那既然用矛盾证法，所以呢，我们就开始就说，这个东西phi transpose phi 它不是 invertible， 最后会导致出来一个矛盾。那推导的过程就是这样。既然呢这个方正它不是 invertible， 那我们知道一个方正它的 rank 再加上它的 neural space 的 dimension 正好就是应该等于这个方正的维度嘛。那既然它不是 invertible， 所以它的 rank 并不是满，所以它势必有 neural space。
那既然有 null space， 它 null space 的维度不等于1的，至少大于1的情况之下呢，所以我们可以找到一个非零的向量，那使得呢这个矩阵乘上这个非零的向量，它会等于0向量，这个是 null space 的定义。那左右两边，我在左右两边能够乘上这个 V transpose， 把它乘在左右两边。那这个数学式呢，直接导下来就是这个 square to norm 的定义。那一个东西的一个 vector 的 to norm 等于0，实际上你可以了解到，就是说它每一个 element 通通都是0。那所以我们得到最后这个结论。那什么是一个矩阵乘上一个 column vector？ 实际上就是把这个 column vector 的这个当成是组合系数，把这些这个在这个 phi 里面的 column 做线性组合。那我们知道这个线性组合呢等于0，但是我们前面又说它是线性独立的，所以这个矛盾就发生了。那所以就是透过这样子的证明，我们就知道在大部分的情况之下也就是呢这个 phi 它有线性独立的 column 以后呢，我就可以确保phi transpose phi 是 invertible，invertible 这边我就可以计算，那我就有 corresponding solution。Okay, so in the log likelihood, we say that the regressor is parametricalized by W. Also, we make the Gaussian assumption. Therefore, we have one additional element to be optimized, which is beta. Beta is the inverse of the variance in the Gaussian formulation. So we use the same technique. We consider log likelihood, and we find that the first term and the third term are relevant to beta. Only the second term is irrelevant to beta. So we can still calculate the gradient with respect to beta and set the gradient to 0. We can get the corresponding solution of beta. Okay, so this is how to optimize W and the beta by using the technique setting the gradient to 0. So finally, let's consider this equation again of the likelihood of the likelihood function. Currently, we have solved W, and we also solved the beta. So we have the ML solution for W and the ML solution for beta. Given a new training data or a new data point as the input, we fit x into the equation. We can calculate its prediction and its variance. So this is how to get the ML solution for the linear model. So far in the first session, I specified how to use maximum likelihood solution to optimize the linear model based on the given set of training data. 这一堂是第一堂课嘛，那第一堂课到目前为止我们做的事情呢，就是给你一个训练资料，然后我定义出来 likelihood function， 然后呢我再取它的 log likelihood， 再针对变数去做微分，然后令微分等于0，我就可以得到这些东西的最佳解，W 跟beta最佳解。那在找出来这些解答了以后，我自然就可以做新的资料的回归Okay, so it is about time to listen up. Let's have a 10-minute break.